So I'm going to be working on a pretty common statics problem, and I'm going to be using Varignon's theorem. It's a really cool theorem that makes things a whole lot easier. You don't have to do cross product. It's just the basic concept of a moment about any point with respect to any force is equal to that force, so magnitude, times the minimum distance, or sometimes they call it the perpendicular distance from the line of action of the force perpendicular to said point. Okay. And what that basically means is if I have this force right here and I want to take it about this, I just have to find this point right here, where it intersects perpendicular to the line of action. That's where you get the, you take this R force or this R vector, and then when you intersect it, again, this is the line of action. This is the theta, and you find this perpendicular distance. That's all it is. Right here, of the line of action. So that's how we get it using the cross product, but there's a much easier way. And what the Varignon's theorem says is that if we break up this force, that we call this force F, into its components, f of x and f of y, and we want to find that moment at some point, and we'll call that point the origin right now because that's what this question is asking for, but it could be any point. Any point, it doesn't matter. So let's just delete that. Basically, the moment is equal to the force times the minimum distance. But Varignon's theorem says that if we break up this f into its f of x component and its f of y component, and we take the sum of those with the d with respect to x-axis and d with respect to y, and so on and so forth, and we sum those up, this would be the same as doing the cross product. So that's what we're going to do here. And so let's delete all of this and let's get to it. So first step is we're going to want to find the components of this force. We call that force F. Okay? You notice that that force F is perpendicular to the arm of the tool. That's not a vector. But we know that this force F is perpendicular to that arm. Right? And if we draw a, actually let's do that in yellow or orange. If we draw an imaginary axis that represents the directions of the x and y, we can see that we know that this angle is 15 degrees. And what would happen if we got this arm right here and we rotated it that way? Well, as this angle approaches 0, this angle right here would approach 0. So that means that this angle and this angle would be the same angle. So now we could say that this right here would be my f of x, which is equal to f cosine 15 degrees. And my y, fy, would be equal to f sine 15 degrees. And I hope that makes sense. So now that we found our components of our force, all we have to do is solve for each force. So we'll pretend like that force isn't there, and we're going to use f of x. Maybe to better illustrate that, I'll try to take this right here, and then we'll take it right there, just so we could be as accurate as possible. So now we can see that f of x is parallel to the x-axis, and f of x, yeah, that's one thing that we should know. So we know that F is 20 newtons, and so we get our values right here of f of x and our f of y. We see that f of x is going towards, if this is positive and this is positive, we see f of x is going in the negative direction, and f of y is going in the positive direction. So that's where we get those values there. But the sign doesn't really matter when using Varignon's theorem. Really, it's all about intuition and using a little bit of logic and common sense. So let's do that. We have our f of x. So notice how I made my table right here. The moment about 0, and this is suppose that we clamp this tool down at this point and it's not able to move. So let's say we have like a ball joint right here, right? And it's not able to be removed from the origin, but it could rotate. It could go this way, it could move this way, it could move this way. And imagine if we released it, it would just flip over and start hanging, right? So that's what we're doing when we're saying, oh, what is this moment about this certain point? So that's what we need to visualize when we're using Varignon's theorem. So let's do that. This f of x. Notice I have my I, j, and k components. And let's see what this f of x does about the x-axis. Now let's imagine that I'm pulling on this with an f of x force. What would happen to this this x-axis, this I-axis right here, this I part? Well, if it's bolted on to right here and I'm pulling it towards the same direction, it's not going it won't go over. It'll just be pulling it in that way. It won't rotate clockwise, or it won't rotate counterclockwise. I know I said that backwards, but it can't rotate about that axis because I'm pulling it in the same direction as that axis. So that's why we have f of x equaling 0 right here. in the I direction. Now let's look at the J direction, okay? In the J direction, what's going on? Well, if I'm pulling this tool again in this direction, what's going to happen is it's going to have the tendency to rotate in that direction. And if we put our thumb in the direction of the positive, we could see that this is going to be clockwise, which is a negative moment. And that's where we get f of x. F of x is 20 cosine 15. And we're talking about this line right here. And what is the moment arm? And if you recall that we have a line of action, right? That means we could place this force anywhere. And if we place it directly on top of the y-axis, we could see that the perpendicular distance to the any point on this y-axis. See, if I stretch this y-axis all the way over here, and I go straight up, I will get that perpendicular distance to that line of action. Now that is going to be our moment arm. That moment arm is the same thing as this distance right here. Now this distance is in millimeters. So I converted it into meters, which is 0.075. And that's how we get a negative, because it's clockwise, 20 cosine 15, which is the magnitude of f of x, multiplied by the moment arm, which is just simply z. Okay? Now let's see what happens when we rotate, when we pull in this direction again. What happens to the z? Well, as I'm pulling it, this tool has the tendency to rotate like this. And if we put our finger towards the positive z direction, we could see that this is counterclockwise, which is positive. So that's how we get this positive right here. Remember, we're still dealing with f of x, one force at a time. And so now we have the sign, which is, we know it's positive. We know that the magnitude of f of x is 20 cosine 15. And now we need the minimum distance. Now remember that the minimum distance is from that axis. The Varignon's theorem says that any point on this axis, so we could stretch this, any point on that axis, right? So if this f of x is parallel to the x-axis, then we could see that let's go to this diagram right here. If we move f of x on top of the y, we see that the minimum distance to the z-axis is just the y. Right there, it's just the y. And I know that may seem a little bit confusing, but let's say, let's look at this f of x, right? And this f of x is going in the same direction as this purple line is, right? Now this purple line I can move up, as long, we just want to find out what f of x is doing to the whole axis. So if we move that purple line up right here, right? Then we could see that the only thing the only minimum distance would be right here, which is the y. The y component. And the y component is just, if this is a 90-degree angle, that y component is just this part right here. And that part right there is just 0.2. 0.2, that looks a little confusing. Yeah. We can see it right here. That y is, this is 0.2 meters. So it's 0.2 cosine 15. And so that's where we get this moment arm right there. Okay, so we're done with f of x, and now let's go to, let's pick a good color that we could see. Maybe not that color. Let's do this color right here. So now let's do f of y. I don't like that color. We need a strong color. Let's do pink. So let's do f of y. Okay? Now f of y at that point, let's see what's going on in the I direction. The I direction. So if I'm pulling it this way, what is it going to do to the x? Let's see. Let's use red. No, that could be confusing. Let's continue with pink. If I'm pulling it, isn't it pushing it in the clockwise direction on this whole x-axis right here? This whole x-axis. This whole thing is just going to be rotating in the clockwise, which is negative clockwise direction. So that's why we have negative magnitude of f of y. Negative magnitude of f of y. And now we need to find the moment arm again. So notice that this force is really along this path, right? And what is going to be the minimum distance from that force to the x-axis? Well, again, it's the z. It's the z distance right here. And so that's why we have 0.75 right there. Okay. Now let's see what's going on in the j direction. The j direction. Now again, if we pull it towards this way, it's just gonna slide across the y direction. It'll never rotate. It'll never rotate. And so therefore, in the y direction, f of y has 0 moment. And in the z direction, all of these, because there is no z component. I mean, f of z component. I'm sorry. I was looking at the wrong thing. Yeah, so in the j direction, it's 0. So now let's see what's going on when this force is being pulled in this direction. What's going to happen to the z? Well, if I pull it, this thing has the natural tendency to move in that direction, and therefore it's also going to move in the counterclockwise direction, which is positive. And that's where we get this positive force, Fy, multiplied by, well, let's think about the moment arm here. Let's do it in a distinctively different color. This moment arm Remember, this is the line of action, so we want the minimum distance, which is just this x component right here, this x. And what is this x? This x is 0.2 sine 15, right? Because if this angle is 15, then this angle is 15, and that means this would be, and this distance right here is 0.2. That means this part right here would be 0.2 sine 15, and that's how we get that moment arm right there. So it's important to note that the minimum distance is the minimum distance from that axis to the line of action. So if we're doing the z, it doesn't matter if the point is down here. It just matters where's the minimum distance from the axis to the line of action. Little bit different, little bit, it seems a little weird, but with practice you'll get the hang of it. Now we've completed f of x, f of y, and we notice that this force F is on the plane. Let's just delete all this stuff that we got here. Delete. So now we see that this force is on the xy plane with a height z, but there is no z component of that force. So f of z is 0. Therefore, a force multiplied by no matter what distance is always going to be 0. Now, all we're doing here is just adding across this way. So 0 plus negative 20 sine 15 times 0.075 plus 0 will give us this value, and then negative 20 cosine 15, this part right here, added to 0 gives us negative 1.448, and this part right here added to this part and then plus 0 is going to give us exactly 4. And now we found the moment with respect to the origin, the moment about the origin with respect to the force F. And look, we didn't use any space. We didn't have to do any cross product, create any vectors. This way is super efficient. And so let's see. What we have here is that we have a negative x, a negative y, and a positive. So this thing looks negative, negative, positive right here. Okay? So that's what this moment about the origin force looks like right there. And to find the direction, coordinate, direction, angle of the moment created, that's really easy to find. Once you have that force, we have all the components right here. It's real easy to find the angles. And really, those angles are just going to be this theta x this theta y and this theta z. Okay, so now I'm going to leave that up to you guys to take care of. It's pretty simple. But now the important part is the moment created by the force about this axis 0 to B. We want to project. Having technical difficulties right now. Okay. We want to project this force about this line 0B, okay? And how do we do that? Well, it's the dot product. Remember that the dot product is really just the projection. If I take let's say I take this, we call this vector OB, right? And I dot it with this moment, we see an angle in between, and we'll call that angle theta, right? And we remember that the dot product between two vectors, let's say v dot or u dot v, is really just u times v times cosine of the angle in between it, right? So if we extend this line towards the back end and we create some unit vector, and we call that unit vector lambda OB, right? And we dot it. Now we see that this angle right here will be the theta, right? This lambda is negative OB, right? It's a negative unit vector. But now we're dealing with so this M respect to F dotted with this lambda OB will give us this value of this line right here, the projection of the moment. But it's just a value. It just gives us this, the length of this, right? But if we want to find the moment as a vector, what do? Well, if we just have a magnitude, don't we have to just only have to multiply by the direction? And that direction is lambda OB again. So that's where we have the moment down here, dotted with the unit vector lambda OB. That gives us the magnitude of the projection of the moment onto OB. And then we take that scalar, and we multiply it by the unit vector again, so that now we create a direction. Once we take that scalar and multiply it by the unit vector again, all we're doing is taking that magnitude and setting it in a direction. I hope that makes sense.